Hi, my name is Alessandro Maggioni and I am the Senior Regional Marketing Manager in EMEA for the Advanced Solution Group in ON Semiconductor. Today we are talking about how our USB Type-C programmable power supplies can satisfy the 5G smartphone fast charging demands. With the emergence of the 5G technology, the telecommunication industry is taking significant strides in advancing wireless architectures. Despite the ever-increasing capacity of the lithium-ion batteries, the rate of the charging of these larger batteries is still improving. If this industry trend continues, USB Type-C's latest power delivery, the PD 3.0 specification, specifically the Programmable Power Supply (PPS) protocol, will become the preferred choice for charging the next generation of smartphones and other portable electronics. Such significant technological advancement require designers to be meticulous in the system design to ensure efficiency and reliability for the end system. In this webinar, we will discuss the latest advancement in charging protocols, power negotiation, and system solution. Here, more in detail, what we are going to discuss today. We will have a look about USB Type-C evolution, so from the evolution of the connector arriving at the USB Type-C, the power contract negotiation down to the PD, and the difference between the USB PD 2.0 versus the new 3.0 protocol. Then we will have a look about the battery size in the 5G smartphones, how is the evolution and the trend from the past till today, and then we'll clarify what does fast charging mean. Then we will explain how we can monitor USB Type-C traffic on a laptop and on a 5G smartphone using the PD 3.0 PPS traffic solution. Then have a look about which are the outlets of the current limit in the PPS, and then a further understanding of efficiency, fast charging and PPS using our FUSB3307 evaluation board connected to the AC input and connected with a DC input. Then we will have a look about the benefit of our solution, which is include the FUSB3307 and our buck boosted NCV 81599, and then some conclusions. Since introduction in 1996, USB has provided unprecedented leadership for the standardization of data communication, charging and power delivery across mobile products. The largest USB technology leap took place in 2013-2016, when the USB committee collectively ratified that the USB 3.1 SuperSpeed Plus, Generation 1 up to 5 Gbps, and the Generation 2 10 Gbps data communication. Power delivery PD 2.0 up to 100 watt or 20 volt 5 amps, and the USB Type-C connector, so the revision 1.2. The 24-pin USB-C connector was designed to handle up to 100 watt with a very compact form factor of 2.4 mm in height. This universal connector offers reversible plug insertion and rotational touch detection, ensuring a cable can never be plugged in backwards nor upside down. Additionally, universal connector reduces the number of cables consumers need to buy in order to connect the various electronic devices. The most significant benefit of USB-C over USB 3.0 for many system designers is the substantial increase in power rating. The USB-C standard power rating is 50 watt, double that of the previous USB 3.0 generation. Implementing the USB-C PD protocol then increases the power capability to 100 watt. While many applications are designed to the standard 50 watt level, more and more system designers are implementing USB-C PD to be compatible with next generation of devices that can handle higher power levels. Before USB 3.1 and the USB-C connector, USB products were defined as dedicated hosts or sources and dedicated devices or SIG. USB charging levels were determined by detecting the voltage on the D+, D- terminals during enumeration. While this methodology works fine up to 7.5 watt, a more sophisticated and robust methodology is needed to safely deliver up to 100 watt or 20 volt 5 amps between a USB source and a USB sink. USB-C PD communication utilizes a single wire protocol between the source and the sink with bidirectional messaging capabilities across the CCP. One use for this PD messaging is to negotiate a power contract. Power contracts are negotiated through a series of messages between the source and the sink to exchange information on their respective system capability. After the source and the sink are attached with an implicit contract at 50 watt maximum, an explicit PD contract up to 100 watt can then be established if both systems are USB-C PD compliant. All legitimate USB Type-C cable must contain an electrical maker, or e-maker, for any power negotiation above 3 amps. A source device that is capable of charging at current above 3 amp will transmit a discovery identity message to the e-maker, called SVID. Sources and sink respond to a start-of packet, called SOP, at the beginning of a received message. In order to avoid collision, an e-maker responds to an SOP at the beginning of a received message to indicate cable compliance. Once the source learns if the cable is more than 3 amps capable or not, the source then advertises its voltage current capabilities to the sink. The sink then requests one of the advertised capability based on its own system capability. If the request is acceptable, the source supplies the grid UPON power. With each exchange of messages, the message received sends a good CRC message back to the message sender, informing the sender that the message was received without errors. So this will ensure the system are communicating through the standard USB Type-C protocol and communication errors are minimized. USB Type-C Power Delivery PD 2.0 allows a maximum limit of 7 power data object PDOs used to expose the power capability of a source device or power requirements of a sink device. So PDOs are transmitted between devices within a PD protocol message across the USB Type-C configuration channel, so the CCP. In contrast to the PD 2.0, the PD 3.0 with PPS offers a range of voltage and current PDOs described in the table. So the PPS advantage is the sink can request voltage and current in a thinner granularity versus the fixed PDOs. So this helps optimize the charging efficiency between the source and the sink. A recently released 5G smartphone has a large 6.9-inch screen and 5000 mAh lithium-ion battery, a 25% increase in capacity over the previous model. Both screen size and 5G were almost likely the driving factor for an increase in battery size. The 25% increase in battery size means more power is required from the AC to DC travel adapter in order to continue advertising the fast charging feature. USB Type-C PPS is the preferred choice of protocol for the travel adapter architecture to accommodate the power demand to realize fast charging. Fast charging is a common industry term that has become ambiguous with common misinterpretation. Traditionally, lithium-ion charging was safely accomplished in a 0.7 C rate. C rate is defined as the charge current divided by the cell capacity. For example, a 0.7 C rate charge current for a 1000 mAh cell is 700 milliamps. Typically, charging time for this battery is approximately 45 minutes time to charge, TTC, for the battery to transition from an empty cell, 0%, to a 50% state of charge, SOC. Charging these battery cells behind the advertised C rate can cause the cell to age prematurely or possibly cause permanent damage. Additionally, such lithium-ion cells are specified by their manufacturer to attain a minimum of 80% of the original battery capacity after a minimum of 500 cycles of use. In order to improve TTC, battery cell manufacturers are designing cells for more than 1 C rate charging, or simply stated, faster charging. This mainly entails lowering the internal impedance of the battery cells in order to lengthen the time the charge profiles remain in a constant current mode, CC, before the cell voltage reaches maximum voltage and the charger provides transition to a constant voltage mode, CV. The table shows
that the 0 to the 50 SoC TTC time can be reduced by 15 minutes by charging at 1C rate versus 0.7C rate. A 1.5C rate will reduce the charge time to 22 minutes, although the 5000 mAh per hour cells require 7.5 amps charging and 32.6 watt peak charger power, so 4.35 volt by 7.5 amps at the battery. The aforementioned recently released 5G smartphone ships with a 25 watt PPS charger and can be paired with a 45 watt PPS charger accessory. Many travel adapters yield efficiency of 80%, which would calculate to a 45 watt rated travel adapter delivering around 36 watt of power to the battery. The charging power of 36 watt is comparable to that of the calculated 32.6 watt, required for 22 minutes from 0 to 50% SoC TTC highlighted in the table. It should be noted that the USB Type-C connector maximum current is 5 amp. In order to achieve a 7.5 amp EBAT, a divide by 2 charge pump would be required between the USB Type-C connector and the battery charger inside the 5G smartphone. For example, if a travel adapter has an output of 10 volt 4 amps, then the charge pump will output 5 volt 8 amp, assuming ideal power losses. This is often referred to high voltage low current, HVLC, considering power dissipation is calculated as power I square resistor. HVLC can yield efficiency benefits to transferring the power from the travel adapter to the phone via 1 meter cable as HVLC instead of low voltage, high current, LVAC. USB Type-C PD facilitated the HVLC system approach and has increased the V-bus maximum voltage from 5 to 20 volt. While difficult to measure the actual internal battery current of the 5G smartphone between the battery charger and the battery, other parameters can be measured. The V-bus voltage and current, E-bus, between the travel adapter and the 5G smartphone can be measured with a USB Type-C PD sniffer. A similar measurements can be done on a laptop, using the same USB Type-C PD sniffer to measure V-bus, E-bus, or USB Type-C PD 2.0. In the example shared below, the ON Semiconductor 60 watt source evaluation board will be connected to a laptop using a 5 amp cable with the USB Type-C PD sniffer in the serial path. The 60 watt source board includes the FUSB3307, USB-C PD 3.0 and PPS fully integrated source controller. The battery of the laptop has been fully discharged for the example. After initial attach, the FUSB3307 source evaluation board advertised the source capability in the form of 4 fixed PDOs and 3 augmented PPS PDOs. The laptop requests the fixed PDO with 20 volt 3 amps, but only requires a maximum of 1.5 amps. The FUSB3307 accepts the request from the laptop, and the power contract is completed. In the plot, the V-bus trace in red steps from 5 volt to 20 volt, initiating the charging in the laptop. The dynamic E-bus current, in blue, ramps up to around 1.3 amps or around 30 watt. Now, the monitoring and the measurement techniques used for the laptop will now be applied for the 5G smartphone depicted in picture, as with the laptop example. The FUSB3307 source evaluation board will be used to charge the phone and create a monitoring path for the USB Type-C PD traffic. So the 5G smartphone initially requests a 5 volt fixed PDO and is granted. Within 7 seconds, the 5G smartphone requests a PPS PDO. So the 5G smartphones immediately enter into an algorithm whereby every 210 milliseconds it increments the requested voltage in red from 8 to 9.28 volt in 40 millivolt steps, while ramping current in blue from 2 amps to 4 amps within around 7-second periods. The 5G smartphone communicates continuously with the FUSB3307 source throughout the entire charger process. Safety is an important aspect of the USB Type-C PD, as the currents and voltages are significantly higher than have been traditionally used in portable electronics in the past. The USB-C PD protocol has a very specific set of standards and guidelines in place to ensure device negotiate power safely and intentionally. One method of communication can be noted in the plot. The 5G smartphone requested source voltage in red ramps from 8 volt to 9.28 volt and has requested a maximum operating current of 4 amps. When the source reaches the 4 amps current limit, called CL, the source sends an alert message to the 5G smartphone to inform the smartphone the maximum level has been achieved. To further understand the alert messaging, this figure captures for the sequential PD traffic, so the index from 672 to 721, before and after the two current limit alert messages were sent from the FUSB3307. Each alert message contains an operating condition bit which informs the 5G smartphone that the source has changed its operating condition from constant voltage, CP, to constant limit, CL. The 5G smartphone then continues its algorithm of 40 mV increment from 90.28 to 9.32 volt. The industry trends of 5G and larger screens are driving the industry to develop larger smartphone batteries based on architecture advancement. Due to these higher power requirements, coupled with the desire of consumers for fast charging, travel adapters need to evolve for this next generation of 5G smartphones. The increasing demand of power output without subsequent improvement in efficiency rapidly lead to the thermal challenges in the end application. As a result, higher efficiency is becoming very more critical, further driving the need for standards such as PPS. If we examine the generic wall-to-battery lithium-ion charging block diagrams, the goal is to provide power to the system, specifically to the PMIC. In parallel, the 1 series cell battery needs to be charged from a virtually empty 3 volt to a fully leveled of 4.35 volt. While several approaches can be used to charge the battery, switching, linear or bypass, the battery charger will always perform at a higher efficiency with an input voltage, here, slightly above the output voltage, here, referred to as VBAT. To further complicate the system, VBAT is difficult to electrically manage for two reasons. The battery voltage rises during the charge profile from empty to full, and the battery voltage rises and falls as the asynchronous load varies. In order to optimize the efficiency, the travel adapter output voltage, here, needs to be tightly controlled by the MCU of the sync device, which now becomes the charging algorithm master. The MCU policy manager can tightly control the protocol messaging and Vout voltage within 20 mV of granularity by reading VBAT voltage via the fuel gauge and sensing the charge pump Vout. With the addition of PPS, mobile device can now charge a larger battery, faster, safer, and more efficiently. The FUSB3307 evaluation board, in the next slides, successfully supported the sophisticated PPS charging algorithm of the 5G smartphones. The FUSB3307 can be used as a USB Type-C PD 3.0 source with an AC input depicted in the block diagram. In this solution, the FUSB3307 operates in conjunction with the NCP1568, an AC/DC active clamp flyback PWM controller. The FUSB3307 regulated VBus across the full USB PD voltage range by controlling the NCP1568 feedback input with his cath output via the FODM8801DV optocoupler. The FUSB3307 also autonomously controls the VBus FET. The FUSB3307 evaluation board here accepts a 4.5 volt to 32 volt DC input and provided 5 to 20 volt USB Type-C PD output, which is compliant with the USB-C PD 2.0, USB-C PD 3.0, and the PPS specification. The FUSB3307 is a state machine-based USB PD and port controller. The FUSB3307 is fully integrated, eliminating the need for an external MCU and firmware development. Firmware development for a USB CPD, USB 3.x, and PPS is not trivial, and it requires comprehension of approximately 1,500 pages of documentation, then digital implementation of the applicable specification. Integrating all of these standards into state machine also makes the system safer from a digital security perspective, which can be beneficial in medical application, for example. Upon soldering to a board within the system, the FUSB3307 will operate autonomously. The state machine within the FUSB3307 include the firmware for the top-level USB CPD policy manager. The FUSB3307 controls the NCV 81599 buck boost by driving the comp input with the ESCAT output pin. Long story short, which are the benefits of the USB 3307 plus the NCV 81599 state machine-based PPS controller versus MCU-based? Plug and play. It is a well-proven solution that can be put into use within your system without the system user knowing or implementing a specific installation or configuration procedure. Note the number of pages in each of the free USB specification here below. This firmware development is not trivial thing to get right. It will take an inexperienced firmware engineer a lot of time, we are talking about months, to develop and get it right. This solution allows customers to move quickly on the market with a ready-to-go solution. And last but not least, it is a wonderful fit for your customer who may not have firmware engineering on their payroll, but want to add USB-C to their product. The conclusion. So USB PD 3.0, which PPS, has quickly become the defining standard for implementing fast charging for the next generation of portable electronics. Not only can PPS deliver 100 watts of power, the very thin voltage and current granularity of the PPS enables higher efficiency for fast charging the 5G smartphone, with 0 to 50% SoC in around 22 minutes. PPS also enables a wall-to-battery control loops architecture where the USB CPD sync becomes the master of a sophisticated and safe charging algorithm with the smart slave travel adapter, using the bidirectional single-wire protocol across the CC contact of the USB Type-C connector. The PPS source operates in higher constant voltage mode or current limit mode, notify the sync with an alert message when changing mode. Charging architecture of the 5G smartphones are clearly trending towards the adoption of the PPS charging methodology. Semiconductor suppliers such as ON Semiconductor have already released autonomous PPS solution for ease of the system integration and eliminated of firmware development. Thanks for your attention. For any question, please let me know. Moreover, the FUSB 3307 evaluation board is fully available and can be ordered at the below link here in the page. Thanks again.